Sorry in advance, this video is probably going to be long, but we're going to go over today how to draw Lewis structures for covalent compounds. You've never done anything like this, and I actually love drawing Lewis structures. This is one of my favorite things that we do all year. I hope you'll like it too. It's kind of like an intro to organic chem, which is pretty much all drawing structures. So, periodic table, get out your notes packet to the covalent bond part, and then, actually you don't need your practice packet open to page 2. You're going to need it. We're going to draw examples, so you might want like extra paper to put the examples on if there's not enough space in your notes packet, but you don't really need that out. Okay, so really fast before we get started, your periodic table, just to make sure, because if you don't have this, you're literally not going to do anything right. You have to be able to count valence electrons correctly. So this column, the group 1, they have 1 valence electron. Group 2, this column, beryllium through radium, has 2 valence electrons. It's the A number. We skip these, and we're actually never going to deal with these. Boron column, they have 3 valence electrons. The carbon column, they have 4, nitrogen has 5, oxygen has 6, fluorine has 7, and then the noble gases have 8, except for helium. Helium has 2 valence electrons. Yeah, whatever. Okay, so you went through the Nearpod. And the difference between metallic, ionic, and covalent bonds. Most of this unit is going to be about covalent bonds, and that's what we're going to be drawing for like the next week plus. So covalent bonds are bonds that occur from atoms sharing electrons. It is between 2 nonmetals, which on your periodic table, nonmetals are the right side of the staircase, so boron, silicon, arsenic, etc. There are some metals that form covalent bonds. Beryllium is one of them. So if you see that, don't let it freak you out. Beryllium acts like a nonmetal sometimes. It's kind of a weirdo. But we're dealing with this side of the periodic table. No transition metals, anything, because we're drawing covalent molecules, which are nonmetals. And they share electrons. So what that means, like carbon dioxide is CO2. In that molecule, which is 1 carbon, 2 oxygens, they are sharing all of their valence electrons together. It's different than an ionic compound, which forms a lattice, like NaCl, because in an ionic compound, Na gives chlorine its electrons. That doesn't occur in covalent compounds. They share them. Like, you know, you share with your brother and sister like you learned in kindergarten. Same thing. Yes, so big difference. And big difference in how they draw them. The part of your notes that say 2 types of covalent bonds, we're going to skip for right now. So we're going to do that after spring break. So I want you to have your periodic table out, and then the parts of the notes that start with, hold on, this, rules for drawing Lewis dot structures for covalent compounds. These rules need to become like your little Bible until you become good at drawing Lewis structures. To draw a Lewis structure for a covalent compound, all you have to do is follow these rules in order. That's literally all you have to do. But people try to go out of order and they mess stuff up. And so we're going to go through and follow these rules and draw the Lewis structure for CF4. Okay, and so you should have this and then somewhere where you can draw your examples out, because I'm not going to leave this on the screen. So step 1, it says count the total number of valence electrons in the compound and divide this number by 2. This tells you how many electron pairs are in your structure. So we're going to draw for CF4. We need to count how many valence electrons there are. Well, carbon has 4 valence electrons. Fluorine has 7 valence electrons. But there are 4 fluorines, so multiply it by 4. 7 times 4 is 28. 4 plus 28 is 32. So there are 32 electrons getting shared in this compound. Now electrons stay in pairs. They stay in groups of 2. So some people like to count electrons by pairs. It doesn't matter. You'll figure out what works best for you. But if we were to count them in pairs, what's 32 divided by 2? 16. So there are 16 pairs of electrons. So that's step 1. Count your electrons, and you have to make sure you count them correct. Step 2. The first atom in your formula will usually be your center atom unless it's hydrogen. Well, the first atom in my formula is not hydrogen, it's carbon. So I'm going to put carbon in the center, and then you just draw the other atoms around carbon. Spread them out evenly, but right now it doesn't matter where you put them. Okay, so they're spread out. Step 3. Connect the remaining atoms to the center using a single bond. So a single bond represents that 2 electrons are being shared. And so what you do is you connect the outside atoms, so these fluorines, to the center by drawing a line, just one line. That line represents a single bond, which means they're sharing 2 electrons. So this carbon and this fluorine are sharing 2 electrons. Carbon and this fluorine are sharing 2 electrons. And this one's sharing 2, and it's sharing 2 down here. So far, there's 32 electrons getting shared in this compound. So far, I have shared, this is 2 electrons, 2, 2, 2. So we have 8 electrons being shared right now out of the 32. Step 4. Add remaining electrons in pairs to the outer atoms first to satisfy the octet rule. What was the octet rule again? Everything wants 8 electrons. And then if there are leftover electrons, you add them to the center atom. So when I say center atom, I mean this. Outer atoms refer to like this. And so we're going to add our remaining electrons, because remember there are 32, and we've only used 8 to make the single bonds, to the outer atoms first. And so what you do, just pick an outer atom. We'll start up here, and we're going to draw electrons around this fluorine in pairs, like this. That's a pair of electrons. It represents 2 electrons or 1 pair. So now this fluorine atom is sharing 2 electrons right here, and it has 2 electrons of its own. So total it has 4. Every atom wants 8, so we need to add more to this fluorine. I'm going to add another 2 here. Now it has 6. And another 2 here. Now it has 8 electrons. This fluorine does. So I can't add any more electrons to fluorine because it has 8. It's good. Let's double count really fast. There are 32 electrons total in this compound, or 16 pairs. So let's count how many electrons we've used so far. 2, 4, 6, 8, 10, 12, 14. Okay, we've used 14. There are 32 left. And so we're going to continue what we did here on the other atoms. So we've used 14 electrons. This would be 16, 18, 20. Now this fluorine is good. It has 8. 22, 24, 26. This fluorine is good. It has 8. And that was 26 electrons. 28 electrons, 30 electrons, 32 electrons. And that F looks funny. So now I put down all 32 electrons. There are none left over because there was 32, and I put down 32, so I don't have any to put on the center atom. And once you put down all your electrons, you need to go check. Does every atom have 8 electrons? Because remember, everything wants 8. Well, each of my fluorines have 6 of their own, 2, 4, 6, and then they have a single bond, which means they're sharing 2. So 6 plus 2 is 8. These fluorines all have 8 electrons. They are happy. Carbon in the center. Carbon is sharing 2 here, sharing 2 here, 2 here, 2 here. So carbon total, because there are 4 bonds, it's sharing 8 electrons. So carbon is good. So fluorine's happy, carbon's happy. I've used all of my electrons. This is the Lewis structure for CF4. We're going to do this again, but with a few more examples. Now, in your notes, there's a section for exceptions to the octet rule. You're going to need to write these down and know these. So, hydrogen can only have 2 electrons. Hydrogen does not want 8, it wants 2. Beryllium has a maximum of 4 electrons. Not 8, max of 4. And remember, beryllium is Be. Boron is stable with 6 electrons. So boron doesn't need 8, it's good with 6. So if an element is not hydrogen, it's not beryllium, it's not boron, it wants 8. It needs 8. These guys can have 2, 4, or 6. Now this one, if the center atom is from periods, which is a horizontal row, 3 through 7, it can have more than 8 electrons. Whenever you look at your periodic table, rows are like this. So if it's from row 3 through 7, it can have more than 8 electrons. It doesn't say it will, it just says it can. And we'll do an example later. And so you can pause the video to write these down and then hit play when y'all are good. So knowing our exceptions, we're going to draw the Lewis structure for water next. H2O. So step 1, count how many electrons are in your compound. Well, hydrogen has 1 valence electron, and there are 2 of them. And then oxygen has 6. So 2 plus 6, there are 8 electrons, or 4 pairs. That is step 1. You have to count your electrons first. Step 2 said, put the first atom in your formula in the center, unless if it's hydrogen. Well, hydrogen's the first atom, so it's not going in the center. Instead, you put oxygen in the center, and just draw hydrogen around it. Let me take this out underneath. Okay, so that's step, let it focus. Step 2. Step 3, connect remaining atoms to the center using a single bond. Done. And now I've used 4 electrons. Remember, a single bond, which is a line, is 2 electrons, and there are 8 total. Okay, now when you see hydrogen, you need to remember the exceptions that you literally just wrote down. Hydrogen can only have 2 electrons. Right now, there is a single bond connecting oxygen and hydrogen. That single bond is 2 electrons. So this hydrogen is happy. Over here, this hydrogen has a single bond, which is 2 electrons. This hydrogen is happy. So we cannot, and you will never put any dots on hydrogen. They will only ever have a single bond next to them, and then they're good. So step 4 says, add electrons in pairs to the outer atoms first to satisfy the octet rule. We're not going to add electrons to hydrogen because hydrogen already has 2, and that's the max it can have. So now it says leftover pairs are added to the center atom. We do have some electrons left over because we've only used 4, and we have 8 total. So we have 4 electrons left over. And so instead of putting them on hydrogen, because it's an exception, it can only have 2, we're going to put them on oxygen. So there's a pair, which is 2 electrons. Now that's 2, 4, 6, and put the other pair here. That's 8. So I put down 8 electrons. There are 8 electrons total in water. Hydrogen each have 2, so they're happy. Oxygen has 4 electrons of its own. It's got 2 pairs. and then it's sharing 4 electrons in each of its, or in the bonds. So oxygen's happy because it has 8 electrons. And that's the Lewis structure for water. Don't need to go any further than that or do anything else. Now you have to make sure whenever you draw Lewis structures that the amount of electrons that you count up in the beginning is how many that are in your Lewis structure. If there's supposed to be 8 electrons and you don't have 8 drawn, it's wrong. No matter what, always no ifs, ands, buts. This number has to equal however many you draw. And remember, a single bond, which is a line, is 2 electrons. We're going to draw 2 more together. CO2, carbon dioxide. Step 1, count valence electrons. Carbon has 4, plus oxygen has 6, and there are 2 oxygens. 6 times 2 is 12, 4 plus 12 is 16. So 16 electrons or 8 pairs. Okay, step 2, put your first atom in the center, unless it's hydrogen. It's not hydrogen, it's carbon. So carbon gets drawn in the center, and I'm going to put 2 oxygens around it. 1, 2. And then you connect the outer atoms to the center using a single bond, which is 2 electrons. Okay, so I've used 4 electrons, or 2 pairs, and there are 16 total. Next rule was add your electrons in pairs to the outer atoms first. So I've used 4. I'm going to start adding them to the outside because oxygen's not an exception to the rule, the octet rule. So I've used 4, 6, 8, 10, 12, 14, 16. Okay, I put down all my electrons. Once you put down all your electrons, go through each of your atoms and make sure do they all have 8 electrons. Oxygen has 8, 2, 4, 6, 8. This oxygen has 8, 2, 4, 6, 8. Carbon, however, only has 4. 2 here, 2 here. So this is not the Lewis structure for CO2. We're not going to erase the whole thing. We can't add any leftover pairs to the center atom because there aren't any more leftover pairs. There are 16 electrons down in the Lewis diagram. So you can't just add more. You have to use whatever number that you counted up in the beginning. So now we're actually going, now that we don't have any electrons left over and the center atom still doesn't have 8, we're going to do step 5. And step 5 says if the center atom is still not satisfied, which means it doesn't have 8 electrons, the electrons you placed on the outer atoms must be brought in and shared with the center atom in a double or a triple bond. And so what we're going to do is literally, and I hope you're using a pencil, you should be using a pencil with this, is erase one of these. And I don't have whiteout right here, so whatever, pretend I erased it. And instead of having that pair on oxygen, we're going to make this a double bond. So a double bond is 2 lines, which is 4 electrons. This didn't take away electrons from oxygen because oxygen is just now sharing 4 with carbon, but it still has 4 of its, 4 of its own right here. So oxygen is still happy; it has 8. But carbon is still not content because carbon wants 8, and it's got 4 electrons here and 2 here. That's only 6. There are triple bonds. Triple bonds don't get drawn often. They're 3 lines, which is 6 electrons. Triple bonds require a lot of energy to make. And atoms are lazy, like you guys. So we could erase another pair from this oxygen and make a triple bond, but that requires a lot of energy. It's less energy to make another double bond because over here we have another oxygen atom. And so instead of making a triple bond over here, we're going to erase one of these and pretend I whited it out and draw another double bond. So now carbon is sharing 4 electrons here and 4 here, and our oxygens still have 8 electrons. They're sharing 4, and they have 4 of their own. So every atom is satisfied by the octet rule. And so that's the Lewis structure for CO2. Now again, we didn't just put pairs on the center atom because there's only 16 pairs total. And if I had erased one of these and put it on carbon, so like let's say I did let's say instead of making a double bond, I just put them on carbon. Now carbon would have 8 electrons, but over here those would have 6, and so that's not an option. That's why we had to erase them and make a double bond. You would only make a triple bond if there was no other option to make a double bond to give the center atom 8. Now, I taught you double bonds. Double bonds are step 5. They're the literal last thing you do. A lot of people want to make double bonds like from the beginning. You only make a double bond if the center atom still doesn't have 8 and like you don't have any other options. Okay, we're going to draw one more together and do this one a little faster because you're probably sick of watching this video. BF3. Okay. Boron has 3 valence electrons. Fluorine has 7. There are 3 of them. 7 times 3 is 21. 21 plus 3 is 24. So we've got 24 electrons for 12 pairs. You write your first atom in the center unless if it's hydrogen, and then just put them like evenly around. Now boron, I hope when you see boron you remember that it is an exception. And the rule for boron is stable with 6 electrons. So boron doesn't need 8. Okay. So connect the atoms to the center using a single bond. Boom, boom, boom. I've used 6 electrons, and now we're going to put them on fluorine. So that's 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I've put down all of my electron pairs. All of my fluorine atoms have 8, so they are happy. Boron. Boron has 6. Boron is, remember, an exception. It's stable with 6, so boron is happy. This is the Lewis structure for BF3. We don't need to make a double bond because boron is stable right here with having 6 electrons. It doesn't need a double bond. But let's say this was literally any other element besides boron right here. If it was something like, I'm just going to make this up. Let's say it was indium. Indium is not an exception to the octet rule. If it was this, you would, and again I'm literally making this up, you would have to erase one and make a double bond to get it to 8. Because it's not an exception, but that's not the case here. With boron, boron's good with 6, so that's the Lewis structure for BF3. You're going to go and work on page 2 in your packet, which is drawing Lewis structures. There are a few things I want you to be aware of. Some of them have charges. I think there's an NH4 plus. If you remember, a positive means that it lost electrons. And so when you count the number of valence electrons in this, nitrogen has 5, hydrogen has 1, times 4, so total that's 9. Because it has a positive charge, you have to subtract an electron. So that has 8 electrons. If something has a negative charge, let's say it has a negative 2, you have to add 2, like this. You would have to add 2 electrons to the total number. And then don't forget about your exceptions. Hydrogen can have 2, beryllium has a maximum of 4, boron is stable with 6, And then if your center atoms from row 3 through 7, it can't have more than 8 electrons. And I just want you to go through and start drawing them following the steps. If you go in order, you won't mess it up, I promise. As long as you count right and you literally follow them. If I were you, draw like 3 and then check the key with Miss Nagley to make sure you're doing them right, because that would suck if you did them all wrong.